Okay, this is 10.8 notes, the ratio test. So before we look at the ratio test, there's two things that you need to recall, and that is how to simplify factorials and how to simplify an exponential. So for factorials, remember a factorial is where you take the number and then you keep multiplying by n minus 1 of that number. So for example, if we had 3 factorial, that would be 3 times 2 times 1. Okay, 5 factorial, 5 times 4 times 3 times 2 times 1, always ending at 1. And so if we have n plus 1 factorial over n factorial, we have to remember that this is the same as saying n plus 1 times n factorial. Okay, again, we're always subtracting 1 after it. So since I have n plus 1, if I subtract 1, it's only n. And then since this is over n factorial, I can cancel out those n factorials and I'm left with n plus 1. Okay, very important that we understand those properties. Okay, so whatever this number is, we would subtract 1. Okay, if it's larger, we'd have to subtract 1 again. And we're trying to get until we only have that n factorial. So for example, if I had n plus 3 factorial, that is the same as saying n plus 2 times n plus 1 times n factorial. I have to subtract 1 every single time until I'm just left with the n. Okay. The other important thing to remember is our properties of exponents. And so 3 to the power of n plus 1 is the same as writing 3 to the power of n times 3 to the power of 1. Because remember, if we have the same base, then we can just add the exponents together, and that's what they did in the original one. And so if I have this dividing by 3 to the n power, then really those cancel out. I'm left to 3 to the first power, which is just 3. So again, very important skills to remember here. Okay, so now let's look at the definition of ratio test for convergence. It says if the summation of a sub n has positive terms, then the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1, then the series converges. Okay, if that same limit is greater than 1, then it's going to diverge. And if that same limit is equal to 1, then we don't know. Okay, which means we need more information. And so this is going to tell us to use a different test. Okay, which means if we try to do the ratio test and we end up with the limit equal to 1, then we know the ratio test is not going to be the test to use. So then we go back and think about all the different tests that we learned. The comparison test, the nth term test, the p-series test, all those different ones to prove convergence versus divergence. So the first part says, let's look at two series we already know. So if we look at number 1, we already know that this a sub n of 1 over n is a harmonic p-series. We already know that a harmonic p-series diverges. Okay, we already know that. We wouldn't have to use any other test to prove this. We already know that about the harmonic p-series. Okay, however, let's see what happens when we use the ratio test. So this is us using the ratio test. So using the ratio test, we have to do the limit of n approaches infinity of a sub n plus 1 over a n. So we're just adding 1 to n. So this is 1 over n plus 1 divided by 1 over n, which is the same as multiplying by the reciprocal. Okay, and when we do that, we end up with n over n plus 1. Using the properties of asymptotes, we know we're just looking at the coefficients here, and we get 1. And remember, if we look at our ratio test at the top, it says if we get 1, then we know the ratio test doesn't work, and we have to use another test. Okay, so all this tells us is ratio test doesn't work. Okay, so let's look at number 2, another one that we already know. So again, A sub n is a P series, okay, where P is equal to 2 and 2 is greater than 1, so we know that this converges. Okay, we know that because of the P series, we have that memorized, which means we technically would not have to use any other test to prove. But again, let's see what happens when we use the ratio test. Okay, so we have to do the limit as n approaches infinity of a sub n plus 1 over a sub n. So this is going to be 1 over n plus 1 squared over 1 over n squared. This is the same as multiplying by the reciprocal. And so what happens is we have n squared over n plus 1 squared, which is just n squared over n squared, which again, looking at the leading coefficients, is just 1. So this tells us the ratio test doesn't work. So notice between number 1 and number 2, okay, these are both types of P series. So we can conclude that the ratio test doesn't work for P series, which means if you have a P series, do not try the ratio test. Okay, you're just going to end up wasting time because you're going to get an answer that is inconclusive, and you're going to have to do another test anyway. So it's just best that you just know the properties for P series. Okay, so now let's look at examples where the ratio test does work. Okay, so number 3, we have the summation of n squared times 3 to the power of n plus 1 over 5n. So for these type of things, the best thing to do is find a sub n plus 1 first, and then we can start plugging it into the limit. So we know that a sub n plus 1 is going to be n plus 1 squared times 3 to the n plus 1 over 5 to the n plus 1. Well, that's the same as saying n plus 1 squared times 3n times 3 squared, because 3n plus 1 is plus 2, over 5n times 5 to the first. So we're using our properties of exponentials to simplify this. Okay? And then, of course, we know a sub n is n squared times 3n times 3 to the first. I'm just separating it just like I did the other one, 5n. And so if I'm doing the limit as n approaches infinity of a sub n plus 1 over a sub n, then I'm going to take my a sub n plus 1, and I'm going to multiply by the reciprocal of a sub n. And then I'm going to see if I can cancel anything out. So from here, I can cancel out the 5 to the power of n. I can cancel out 3 to the power of n. And I can cancel out one of these 3. So I still have a 3 there. And so simplifying this, I have 3 times n plus 1 squared over 5n squared. And so really, what I have, because I only really care about the highest exponents in each one. So this is going to be 3n squared over 5n squared. Okay, and I only want the leading coefficient, so this is going to be 3/5, and we know 3/5 is less than 1. So based off the ratio test, then we know that this is going to converge. So therefore, the series converges by the ratio test. So this is an example where the ratio test does work. We did get a number that is less than or greater than 1, and we're able to prove converging or diverging. Okay, let's look at number 4. So number 4, we have a factorial in here. So our first step is just like always, we're finding a sub n plus 1. So a sub n plus 1 is equal to 4 to the n plus 1 over n plus 1 factorial. Well, that's the same as saying 4 to the power of n times 4 to the power of 1 over n plus 1 times n factorial. Okay, and we know a sub n is just what they gave us up there, and I can't simplify that in any way. So then I do the limit as n approaches infinity of a sub n plus 1 over a sub n. So this is 4 to the power of n times 4 to the power of 1 over n plus 1 times n factorial times the reciprocal of a sub n, which is n factorial over 4 to the n power. So the factorials can cancel out, 4 to the n power cancels out, and I am just left with 4 over n plus 1. Okay, so as the limit as n approaches infinity, okay, the denominator is going to be larger than the numerator, so this is going to approach 0, and since 0 is less than 1, I know that this series is going to converge due to ratio test. Remember, this is our justification. We have to include that at the very end. Okay, we have one more example here. So let's look at number 5. Okay, number 5, we have another factorial problem. So again, our first step is to do a sub n plus 1. That is the same as doing 2 times n plus 1 factorial over n plus 1 to the 5th power. That's the same as writing 2n plus 2 factorial over n plus 1 to the 5th power, which is the same as saying 2n plus 2, subtract 1, 2n minus 1, subtract 1, 2n factorial, all over n plus 1 to the 5th power. Okay, now we do a sub n, which is just the same thing we see up there. Okay, we can't simplify that factorial any further because it's just n. It doesn't have any constant at the end of it. So then we're going to do the limit as n approaches infinity of a sub n plus 1 over a sub n. So we have 2n plus 2 times 2n minus 1 over 2n factorial, times 2n factorial, over n plus 1 to the 5th power, times the reciprocal of a sub n, so that's n to the 5th power, divided by 2n factorial. Cancel some things out. Okay, notice we can even cancel out here because that's just going to be n to the 5th power plus some constants of n that have lower degrees. Okay, so that doesn't really matter. So really what we have is we have 2n and another 2n, which is going to give us some form of n squared. Okay, there's nothing left on the bottom, so I say this is over 1. So if we do the limit as n approaches infinity, that means we're going to have infinity over 1, which is infinity. Infinity is greater than 1. Therefore, this series is going to diverge due to the ratio test.